So what was the conclusion last time? So the conclusion last time was that we had this notion of learnability. We have two notions. The back learnability made a strong assumption that we have the target function in our class, and agnostic learnability that made much less assumptions and was a little bit weaker conclusions. And we proved, I mean, I think I proved that two results, that if H is finite class, then both of them are learnable. They are learnable in the agnostic sense and in the learnable in the use. We also had one negative result, and the one negative result was that the set of all functions is not learnable. So what I want to start with now is trying to have a sharper distinction between what is learnable and what is not learnable. This is one of the basic questions that we should ask in such a situation. We have some examples of learnable classes. We have at least one example of something which is not learnable. How could we distinguish between the two? So the first candidate is to say finite classes are learnable, maybe only finite classes are learnable. I mean, if that were the answer, then things would have been very boring. So some infinite classes are learnable, and since I'm willing to go a little bit more into technical stuff here, let me show you why initial segments on the real line are learnable. So my class is the class of all initial segments of the real line. So we have the class H, let's call it H initial, and it's the set of all HR such that R is a real number. And it is defined that HR of X is 1 if X is at most R, and say 0 otherwise. So this is a class of, for every real number R, I have a function that says it's going to be 1 up to this R and 0 above. Right? So let's say I want to distinguish what are, I want to have a class of all the, learn who is considered to be short. So I have some, I'm trying to learn this expression. Okay, now clearly this class is infinite, and I want to show you that this class is agnostic Pak learner. Because we want an example of at least one infinite class which is the agnostic Pak. So I have to show you some kind of a function, m, h, of epsilon delta, such that regardless of the distribution, if you see so many examples, you have a very good chance, at least 1 minus delta, that you will come up with an error of less than x. So how should we argue? Now, remember that before, our argument was for every single h, we have uniform convergence, and then we take a union bound over a finite class. But if we take a union bound over an infinite class, the probability, I mean, the union bound is, say, the probability of making error on some h is the sum of the probability of making error on all the h's. If the sum is infinite, we'll get a bound which is meaningless. So we have to work in a different way. And the trick is as follows. So assume, so here is my real line, and assume that this is the target function. So this is the function f according to which we label. So it labels 1 here, and it labels 0 everywhere here, and we are trying to learn this function, and we are getting examples labeled according to this function by some unknown distribution. So now let us analyze what can happen, what can mislead us. So we are going to get points here, all labeled 1. And we are going to get points here, all labeled 0. And when are we going to make an error which is bigger than epsilon? That's what we have to analyze, right? So what we can do is say, if this is the real, say this is R star, this is the real threshold that determines the unknown function, then we will take an interval of weight. I don't know what the distribution is, but just for the sake of the argument, I will take an interval that has weight epsilon to the left of this threshold, and I will take an interval of weight epsilon to the right of this threshold. Note that Intentionally, I made them of different lengths, because it's not length epsilon, it's an interval that is big enough such that the probability, which I don't know about, will place epsilon weight on this interval. So I go as far as I'll get probability of epsilon of hitting. Okay? So this is just a virtual construction. We don't know. Now we want to analyze which samples are going to mislead the ERM algorithm. So what I'm claiming is that if we got a point that was here in this interval, and we got a point that was here, then our error of any ERM hypothesis will be less than it. Because if I have a positive point here, and I have a negative point here, and I pick any assumption that is consistent with these points. So what I will pick is some hypothesis H that will sit here. And what is the error of H? Here H doesn't make any error because here H predicts +1. Here H predicts 0, so where does it make an error? It makes an error, let me use a different color. Where's my red? Okay. So this H is going to make an error only here. And this has weight less than epsilon, because I fell inside the epsilon interval. So if I'm sitting inside the epsilon interval here, and I pick a hypothesis which is consistent with what I saw, then my error is less than epsilon. Similarly, if I see a point here which is within this epsilon bound, then if I pick an ERM H, I can pick a different H, say I can pick this H. But this H is going to, where is it going to make mistakes? This H is going to predict 1 here and 0 here. It's going to make mistakes only here, and this is also less than. So the conclusion is that if the sample S contains points in both epsilon weight intervals, then any ERM H that is applied to this sample has error less than epsilon. If I have a point in each of those two epsilon margins on both sides, then my error of any ERM hypothesis is going to be less than epsilon. Is it clear, or my handwriting is not clear? But I see people stretching their heads as if you become, oh, I had to, is it helping? Yes. There is some unknown distribution. I don't know those intervals. There is some unknown distribution that generates the data. And I look at this unknown distribution and I define, without knowing where it is, I define these two intervals. One of weight epsilon to the left of the true target, and one of weight epsilon to the right of. And the main argument is that right, so these are my crucial intervals. This is one interval here, from here to here. That's the interval to the left of the target, and then I have this interval to the right of the target, and each of them weighs epsilon. If I have a sample point in each of them, then a consistent ERM hypothesis will make error smaller than it. So my probability of making an error bigger than epsilon is the probability that I will not hit this guy, and I will not hit this guy. But now notice, we took the infinite class that we had, and we reduced it to just two events. Not hitting this guy, this is a guy of weight epsilon. And I take m samples. Every single sample, the probability of not hitting, so the probability of the error with respect to p of this ERM H of S is less or equal than the probability that I will not have those 2 points, right? But not having a point here, we already analyzed it. This is an interval of weight epsilon. Not having a point here is at most 1 minus epsilon to the power m. I pick m independent points. Each of them has probability 1 minus epsilon of not hitting this interval, so that none of them will be there. It's the intersection of this one will not be there, and this one will not be there, and this one, and each point was picked independently. So this is the independent argument. It's the product of all. That's not hitting the left side, or not hitting the right side, so it's plus 1 minus epsilon to the m of not hitting the right side. But if I did hit both sides, then I'm good. So I get here, this is at most 2 times, and each of that is 1 to the minus epsilon m. And the main point is that as m goes to infinity, it doesn't matter what epsilon is, this will go to 0. So if I want this to be less than delta, I can pick m, which is just a function of epsilon and delta. So we show that this class is learnable. So we have here an infinite class. We managed to show it's learnable because in some sense, we reduce the case of missing each of the h's to just 2 sets. Yes. We're realizable. I'm analyzing the realizable case. That's a good point. Just for simplicity, I'm analyzing the realizable. Right. But we could have made a similar argument for the agnostic case. So there is something interesting here that it's not about the finiteness of a class. You remember last time someone asked me, what about the structure? So here we see a class that has enough structure that although it's infinite, I can bound the probability of making an error. Are there any more questions here? Yes. Right, it could be, that's a good point. Could it be infinite? So if the probability of being here, what does it mean infinite? That in order to get weight epsilon, I have to go all the way to minus infinity, which means that the probability of seeing a 1 is less than epsilon. In that case, I'll just predict 0 everywhere, and my error will be less than epsilon. So those cases, those extreme cases, are easy cases. If all your sample are just zeros, you predict 0 error. Any other questions? Yes. Yeah, so the question is, how can we generalize this property? That the zeros cannot be in. Yeah, I mean, somehow intervals, these initial segments are simple. But in what exact sense is it? So that's what we want to analyze now. We want to find a distinction between cases in which the structure is simple and cases in which the structure is complex, but how do I define this structure? So let me contrast it with another example that has the same cardinality. So let us look at another example and just see what do you think of this other example. So there is also the class of all singletons that I leave to you as an exercise. So singletons are all the functions that give 1 only to a single point and 0 everywhere else. So there are, of course, infinitely many such functions, because the function can give 1 in any given point. But each function gives the value 1 only to 1 point. This class is easily learnable because if we just see zeros, we will just say everything is 0. And if the 1 had a weight, at least epsilon, we should have seen it if we have enough samples. And if we see a 1, we know everything. This is my 1, everything else should be at 0. Again, it's a realizable case. So both classes are infinite classes that are learnable, although in the realizable case, although they're infinite. Yes. In a second, I will talk about it. In a second. So, I mean, I'm glad that you are, well, what he's asking is he's trying to guess how can we extend the learnability to more classes, right? And that's exactly what we're going to do. Yeah. Right. That's fine. I don't mind. So what he's saying, assume that my domain is the real line. And my domain is my functions, and my domain is the real line. And I have some unknown target function that at one point gives a value 1 and everywhere else is 0. So what he's saying, oh, I'm never going to hit this one. How will I know where this one is? But note, what is the answer? How do we overcome it? Right, but we can be even more precise about it. What? So there are two cases. We are sampling from this distribution. There are two cases. If this point has a high weight, then I'm going to see. If it is a lower than epsilon weight, then I don't care. Because I will predict 0 everywhere, and that's going to be less than epsilon cases where I'm going to make a mistake. Okay? So the trick here is the sample is generated by the same distribution on which we are tested. So if the distribution on which we are tested doesn't care about this point, I will not see it in the sample, but I don't care that I'm going to miss it. If a distribution does care about this point, I'm likely to see it in the sample, and I will not make it. And that's part of the flavor of this SPAC thing. We are trained on the same distribution that we're going to be testing. Where did I leave the? Oh, this one. So we have two examples of infinite learnable classes. Let me consider another example, which is kind of in the spirit of what you were asking. So what do you think of the class? Instead of one peak, assume that the class is allowed to have finitely many peaks. So let H, another example, let H finite be the set of all functions f going, say, from the real line to 0, 1, for which f minus 1 of 1 is finite. So what does it mean? It's the set of all functions that are 0 everywhere, but I allow a finite number of 1s. But I don't tell you how many 1s there are going to be there. I'm just saying it's a finite number. Now, what is your guess? This H finite, is it going to be learnable or not? So who dares to voice an answer? I mean, you can enjoy your anonymity. I don't know your name. Most of the friends don't know your name. Yes. What do you say? You think it's learnable? Let's be democratic. We know after the elections in the US and Brexit how useful democracy is. So who thinks that it's going to be learnable? Oh, there's a big majority. Okay, so it's like the other example that I mentioned. It's not learnable. and the reason is that we can look at our no free lunch argument. So I'm claiming this is not learnable. And to prove it, I'm going to apply my no free lunch argument again. So what was the no free lunch argument? The no free lunch argument, actually, we can view it like this. If I have, where are we? Oh, it's just that someone was nice to me, and I mean, it's not someone, it's nature was nice and turned off the lights. Oh. So what did I prove? So if I go back to the no free lunch argument, what did I need in order to carry that argument through? I needed that if there exists some domain set A, subset of the domain, such that every 0, 1 behavior over A is is realized by some h in h, then mh of 1 over 7, 1 over 8 is going to be at least the size of A over 2. So this is a slightly stronger statement than what I proved. What I proved is that take a domain X, and if you want to achieve this, and you have all functions over X, and if you want to achieve this type of success, you will need at least X over 2. But what I'm saying is that it is enough that I have a subset that has all possible functions over this subset, because then I can have my distribution of points, of instances, to just be over some subset. I don't mind that it's not all over X, right? If this is my X, and I have here a subset A, and I want to apply the no-free lunch argument, I will just look at the distribution which is uniform over A and ignores the rest. And now I can repeat exactly the argument of the no-free lunch, because this A serves as the X that I had there, and I need at most the domain over 2 points. The only thing that I used was the fact that over this domain, I had all possible 0, 1 behaviors in my class. Because when we built this counter argument, we said there is the algorithm. Whatever the algorithm predicts, on any point that you didn't see, half the functions will predict the opposite. So the no-free lunch argument, although we were very squeezed in time when we did the proof, the point to take home from there is that if you have a set over which all behaviors are possible, you need to see at least half of it to be able to learn. Because if you saw less than a half, since all behavior are impossible, on every point that you didn't see, there are all the options, zeros and ones, and no matter what you predict, half of those options you're going to miss. Okay? So we strengthened a little bit the no-free lunch and said it's not just about the class of all functions over X. It's enough to have a subset such that I have all possible 0, 1 behaviors over those subsets. Now let's go back to the class of all functions that have finitely many ones. I mean, someone there, which we don't know his name, and he doesn't want us to know his name, was claiming that this is learnable. If it is learnable, then you must have some m, which is this m h of 1 over 7, 1 over 8. This is the delta, and this is the epsilon, or the other way around. Right? So you must have such an m. If you claim that you have such an m, I will take a set A of size 3m, some A. The set of size 3m is still finite. If it's finite, then my class of finitely many peaks can have all possible behavior. I can give all of them 1, because there are only finitely many of them. I can give some of them 1 and some of them 0. Because I have the flexibility. I can, in my class, I have every function that assigns at most finitely many ones. And my set A is still finite. But my set A now has all possible behaviors, and it's more than twice the size that you thought will suffice. So we got a contradiction. So the class of all functions that have at most finitely many ones is not learnable. Is it convincing enough? Yes. Of fixed bounded length. The probability of the support is fixed. Okay. Okay, the cardinality. Then we will be able to learn. Yeah. Okay. So where are we? Let us, I mean, I think that we are without slides, but I can manage. So let us just summarize where we are and see what the challenge is. So what we've seen is, if I want to summarize what we have, what is learnable and what is not learnable. What is learnable, we know that we have any finite h's. We have the class of all initial segments. We have the class of all singletons that have at most one point where they give 1. And in a not learnable, we have the class of all functions over infinite x, but we also have much smaller classes, the class or h finite over, say, R. Yes? Right. This is a bigger class. The bigger the class, the harder it is to learn. Singletons are functions. Singletons are all the functions. Singletons are the set of all f going from x to 0, 1, such that f minus 1 of 1 has size at most 1. It's a subset of all functions. And what I'm saying is that it's harder to learn a bigger class, because just look at the two cases. The case of agnostic learning, learning a class meaning I can compete with anybody in that class. Right? I can guarantee that my algorithm does as well as the best in the class. So if the class is bigger, it's difficult to do as the best in the class. If the class is bigger, I have more competitors. So this is a smaller class, this is a bigger class, so it makes sense that although the smaller class is learnable, the bigger one is not. I mean, this class has everything. You want to compete. If you want to compete with everybody, it's too much. You cannot do it. If you want to compete with a limited set of competitors, I can guarantee that you will. Make sense? So a class is a fixed subset of functions. So I'm saying some subsets are learnable, some other are not. So now we are trying to find a criteria that will distinguish learnable from non-learnable, and we have candidates that basically what they show us is that the size doesn't matter. It's not about the size, right? Because if you look at, I don't know how familiar you are with the cardinality of infinite sets, but what is if this is singletons over the real line, what is the cardinality of this set? It's infinite. But what kind of infinity? What is it? Not aleph 1 is the continuum hypothesis, but the cardinality is 2 to the aleph 0, or the cardinality is the cardinality of the real line. It's the same size as the real line. And what is the cardinality of h finite? Same cardinality, 2 to the aleph 0, or the cardinality of the real line. So what I'm saying is, even if we take into account small infinities, big infinities, and try to ask ourselves, maybe one of them is a big infinity and the other one is a small infinity, both of those classes are the same infinity. So even if we do the more sophisticated measure of not just saying infinity, but trying to figure out which infinity is, we have two classes of the same infinity. One of them is learnable and one of them is not. Yes? H fine, well, inverse of the set of points that are mapped to 1 is finite. Right? So it's not difficult to see that this class is also the same cardinality as the real line. Okay, so cardinality is not what matters, and that is a very big was a very big open question. And this open question was answered by those two Russian mathematicians that Bernard mentioned in the morning, Vapnik and Chervonenkis. So there were statisticians working in Russia, and they discovered this in, so this kind of result that characterizes what is learnable and what is not was discovered by Vapnik and Chervonenkis in 1971, and then rediscovered by a group of American people, BEHW. I mean, these are just the acronyms. Blumer, Ehrenfrocht, Hausler, and Warmuth in 1986, independently. But that was the world of before archive and before email and before everything. So you could have two independent big discoveries of the same thing 15 years apart. And they kind of found a characterization of, oh, thank you very much, not my email. Okay, so let us go back a little bit to the slides, and then anyway, I mean, I prefer when I do more technical stuff to do it on the board, so somehow I have better control over the time. I don't rush. Okay, so we had the class of finite subsets of an infinite domain. We have the class of initial segments, singletons. We have examples of classes which are learnable, and we have this class which is not learnable. So what is this distinction? Okay, so we have to introduce now combinatorics. So until now, all we did so far was just statistics. We were just looking at probabilities and using some basic ideas of probability. And now you will see that machine learning theory, actually, it combines 3 or 4 areas of mathematics. So there's the probabilities we saw so far. Now we are going to see combinatorics. We're going to forget about probabilities for a while. Then we are going to see some linear algebra. And then we are going to see some complexity theory. I mean, as much as time allows. But it's one of the nice things here is that you can play games between different areas of mathematics. And now we are switching to the combinatorics. So these are very nice combinatorics. So I want to distinguish between a complex class that I cannot learn and simple classes which I can learn, and it's not a size. So I have this notion of shatters. I say that say a class H shatters a domain subset A if for every subset B of A, I have some function in my class H of B, so that this H of B gives value 1 for all points in B, and gives value 0 for all points in X in A minus B. So if I draw it again, I'm saying that a class shatters a set if I can cut out every subset of this set. So here, let us look at an example. So assume that my class, let H be our initial segments again. And I'm claiming that initial segments are very poor at shattering. If I pick one point, this is my set A. A is just 1 point, say just the 0 point, or just the point 17. 1 point. This is the point 17. Then, how many subsets do I have of A? 2 subsets. I have B1, which could be the empty set, and B2 could be the full set. And I can find an H that cuts from here, that has just the, nobody gets a 1. So the empty set gets 1. The set of all functions, of all points that get 1 is exactly the empty set. Or I can have the threshold here, and it will get a 1. So this set is shattered. But what will happen if I take two? If I take a set A prime, which is going to consist of 2 points, say the point 2 and the point 5. Can I shatter it with initial segment? Can I get any possible 0, 1 behavior over these 2 points with initial segment? Which behavior is going to be missing? Yes. I think it was your voice. It was you, right? Yeah. Okay. So what behavior is going to be missing? Right. Right. So if I have here the point 2 and here the point 5, I cannot have any function in my class that will give a 0 here and a 1 here. Because all my functions are initial segments. All my functions, they pick a threshold and they assign 1 to the left of this threshold. So if I assigned 1 to this point, I should have assigned 1 to 0. So this behavior is excluded. The set B, which contains, this is my A prime, the set B, which contains only the point 5 and not the point 2, cannot be realized by a function in my class. So the class of initial segments shatters sets of size 1, but it doesn't shatter any set of size 2. Let us look at another example, a little bit more interesting geometrically. So let H be the set of all rectangles in R2, all axis-aligned rectangles. So it's the set of all axis-aligned rectangles in R2. So it's the set of all functions. So one function, it's 1 inside and 0 outside, and I can pick any rectangle that I want. And now I want to see what does this class shatter. So the class is clear what the class is? It's all the functions that pick a rectangle, give 1 inside the rectangle and 0 outside. So, and this is kind of a very natural class. So I want to tell you, if you are healthy and I have 2 parameters, which is your blood pressure and your heartbeat, and I tell you you are healthy, if your blood pressure is between this and this bound, and your heartbeat is between this and this bound, so you're in a rectangle in this space, you're healthy inside, you are unhealthy outside. Okay? So that's my class, but I have in my class all possible rectangles. Now let's see what we can shatter and what we cannot shatter. So what if I take 4 points, this is R2, and I take 4 points that look like this? Can I shatter them with rectangles? Can I get for every subset a function which is 1 on this subset and 0 outside? Here I can, because of course I can have this rectangle that will just give everybody 0. I can have this rectangle that give everybody 1. I can have this rectangle, and I can have this rectangle, or this rectangle. For any subset, I can pick a rectangle that will cover this subset and miss the rest of the set A. The set A is just 4 points. But on the other hand, can you show me even a set of 3 points that I cannot shatter? Yes? Yeah, 3 points in a line. If I pick here 3 points in a line, say this is my set A, suddenly I cannot shatter it, because I cannot have any rectangle that will pick this guy and miss them certain one. So shattering means this set of points gives me the full flexibility of my, I can get any behavior if I shatter it. If I don't shatter it, some behaviors are missing. Okay? That's the notion of shattering. So now let's move to the next step in our characterization. Okay, we did some examples, and now we define the Vapnik-Chebonenko dimension. So the Vapnik-Chebonenko dimension of a class is the largest set A such that A shatters the class. So this is a very important definition, and notice that there's no statistics involved. We are just doing combinatorics. We are just looking at behaviors or functions over my domain. So the Vapnik-Chebonenko of the class is the size of the largest set that I can shatter. Now, why is it going to be, I just promised you that I'm not going to do statistics, but I will just remind you the statistics that we've already done. Why? We already can see that there is a connection here with learning. Because if we look at the argument that I did for the non-learnability of finite support functions, we already saw that if a class H shatters a set A, then we know that MH for 1 over 7, 1 over 8 should be at least what? The size of A over 2. If I shatter a set A, it means over the set A, I behave as if I have all functions. So the largest set that I can shatter gives me a lower bound on the sample complexity that I'm going to need. So in particular, if H has infinite VC dimension, then H is not learnable. Because if H has infinite VC dimension, it means that when I look at the largest set that I can shatter, I cannot find a finite number. Like for every number, I can shatter a bigger set. This means infinite VC dimension. There is no supremum. There's no maximum here on the sizes. So I can shatter arbitrarily large sets. So whenever you tell me M of 1 over 7, 1 over 8 is 1,000, I will find a set that I shattered of size 2001 and look just at behaviors over this set and use the no free lunch, and I showed you that your 1,000th point did not suffice. Okay? So we already see one connection between this combinatorial notion of shattering and learnability. But this notion is much fun on its own, so this was just motivation, but we will now a little bit discuss just this notion. But is the argument here clear? That if we look at what we actually did in the lower bound, in the non-possibility, non-learnability result, we actually just looked for shattered sets. Okay, so we have this notion of VC dimension, which is the largest set that we can shatter, and let us look at some examples of the VC dimension, because this is such a central notion. It will turn out that it's completely characterized learnability, VC dimension. Not only characterizes what is learnable and what is not, but it also tells us exactly what the sample sizes that we are going to need. So it's an important notion, worthwhile to look at examples. So what examples do we know so far? What is the VC dimension of H initial? This is something we already know. What do you think? 1. And saying that this dimension is 1 means there is a set of size 1 that I can shatter. In fact, every set of size 1. And I cannot shatter any set of size 2. So the maximum here of all the sizes that I can shatter is 1. What do you think is going to be the VC dimension of H intervals? If I'm going to look at intervals over the real line, so my class consists of all functions that pick an interval, give 1 inside the interval and 0 outside. And I can pick any interval that I want. How much can I shatter and what can I not shatter? I can shatter 2 points, because if I have 2 points, I can have an interval that picks only this guy, or an interval that picks only this guy, or an interval that picks both of them, or an interval that misses both of them. But if I pick 3 points, I don't have any interval that will pick the 2 extreme points and not the center. So I cannot shatter any set of size 3, and I can easily shatter sets of size 2. So intervals have VC dimension 2. What about the VC dimension of rectangles H in R2 rectangles? Axis-aligned rectangles in R2. Okay, now we have at least some action. I mean, 2, 4, anybody for 3, anybody for 7. Right. So the visible dimension of rectangles is going to be 4, and for that I have to show you a set of size 4 that is shattered, and I have to convince you that no set of size 5 is shattered. I don't bother with the fact that there are sets of size 3 that are not shattered, because I only care about the biggest side that I can shatter. So this is going to be 4, because we saw that we can shatter a set like this. We can shatter a set that looks like a diamond, the corners of a diamond. But if I have 5 points, can anybody argue why can't shatter any A of size greater or equal 5? Why rectangles will not be able to shatter any set, no matter what the configuration, if I have 5 or more points? Yeah, but we want to prove. It's a good point. You want to argue this? That's a good point. Right, so the best way to see it is to say, assume that I have some collection of points that I am trying to shatter with rectangle. I will take the point that is leftmost, and I will take the point that is rightmost, and I will take the point that is bottommost. So I'm picking the extreme point and the topmost point. Now I'm claiming any rectangle that contains these 4 points must cover all of my A. So if there are any further points in my A, I cannot separate them. I cannot take these 4 extreme points and not the center. So whenever I have a set of size more than 4, I will pick the rightmost point, the leftmost point, the topmost, the bottommost. I just pick 4 points. If I cover these 4 points, I'll have to cover everything. So if these 4 points are not everything, I'm not shattering, because I cannot cover them and miss the rest. So rectangles have this is dimension 4. What do you think about singletons? This is dimension of singletons, H singleton. Anybody? This one is an easy one. I'm allowed to only assign a single 1, and the rest is 0. So what can I shatter? Only 1. I cannot shatter 2 points because I cannot cover the 2 points. For shattering, I also need to cover the full. What is the VC dimension of H finite? All functions that have finitely many points labeled 1 and the rest labeled 0. What is going to be the VC dimension now? Infinity, because every finite set can be shattered. Every finite A is shattered because every finite A I can have all behaviors. So if I looked for the maximum size of a shattered set, there is no maximum. So the VC dimension is infinite. So we begin to see a pattern here. And the pattern is that classes of infinite VC dimension are not learnable, but on the other hand, classes of finite VC dimension are learnable. So it turns out that this magic parameter is a complete characterization of what is learnable and what is not. So let's see over how many slides did I spread this result. Okay, so this is what we always said. The proof of the no-free-lunch theorem showed us, in fact, that for any class, the number that I need for 1818 is at least the VC dimension of 2. So the VC dimension gives me a lower bound on how many examples I'm going to need. And as a corollary, if the VC dimension is infinite, then I cannot learn the class. Now what is happening in the other direction? Now this is the beautiful theorem, which is called the fundamental theorem of machine learning. And this is a qualitative version. And it says the following. The following 5 conditions. We talked about all of them. I mean, you wouldn't believe. I mean, we are only here a couple of hours, and we already covered these 5 notions, and you should somehow have a feeling of what each of them says. First of all, H has uniform convergence property. You remember, uniform convergence was that if I take large enough samples, then they represent every member of H. We know that uniform convergence implies that ERM is a good agnostic learner. We made this argument. If you have representative samples, then you do ERM over those samples, and you get a good learner. Then the class is agnostically learnable. If it is agnostically learnable, it's also PAC learnable, because this is a weaker condition. This is only learnable in the case that the labeling is in the class. And this implies finite VC dimension, because I want to show you that D implies E, but we just argue that not E implies not D. If you don't have a finite VC dimension, or VC dimension is infinite, you're not learnable. So now the claim is that all these conditions are equivalent. And I just showed you that A implies B, B implies C, C implies D, D implies E. What is missing to get the full cycle here, that everybody is equivalent? E implies A. That's the hard. But we already have 5 differently looking conditions, and now we are going to claim that all of them are equivalent. And the nice thing is that this condition is completely combinatorial. I can check it on a class without having to do any statistics. So all the statistics goes into proving this theorem, but then I don't have to worry about it anymore, and I just can do combinatorics on the. Okay, so the next step is I want to give you some flavor of this proof. I'm not going to do this proof. This proof is in fact, the reason that I got into machine learning, because, I mean, I don't know to what extent I have to tell stories here, but I was doing logic, and I got my first position as a professor, and they put me on an exam of the student. The student wrote a thesis which cited this theorem, which of course I didn't know about it against logic. And as some students do in their PhD, they don't give good citations. So it got the feeling that it's the student that proved the theorem. And I look at the student, it's not you, and I said, I mean, the guy doesn't look so smart. It doesn't make any sense that he proves this theorem. So I said, okay, therefore it must be wrong. So I went home and thought hard and found the counterexample. So I come to the exam and say, oh, this is wrong in your thesis, here is a counterexample. So everybody jumps at me. What? This is Vapnik and Shovanenkis and Blumer, and this is the most important theorem. How did you find the counterexample? So I wrote to all these people and told them I have a counterexample, and they invited me to talk to them, and I got to the conclusion they are nice people, and I switched to machine learning. So there is a counterexample to this theorem, but the counterexample relies on set theory, and I continue my processes, and for normal people, it doesn't matter. There is a proof that holds under reasonable conditions. They just were not careful enough about the conditions. Okay, so we are going to talk somewhat about this proof of the other direction. Why does E imply A? So for that, we are going to do a little bit more combinatorics. And this is very nice combinatorics. And so we keep ignoring statistics. My students in my classes in Waterloo, they're really happy when they don't have to do statistics. I don't know about you. Okay. So I want to define this interesting function. And this is the shuttle function. It's a function that goes from the natural numbers to the natural numbers. And it depends on a class H. So I have a class H, and I defined pi H of a number M. So you see the function pi H depends on H. But it's a function that takes a natural number and spits out a natural number. So when I take a number M here, it gives me the maximum number over all sets of size M, the maximum numbers of behaviors of H over A. So I denote by this H restricted to the number of 0, 1 behaviors that H has over A. Okay, so again, H, let me again draw it. If I have a function, if this is my domain X, and I pick here some subset A, and I have here all kind of functions in my class, H restricted to A is just the behaviors that I see. So if I have two functions that behave the same here, but differently outside, it is only one behavior over A. So for a function H restricted to A, you just check what 0, 1 it gives to members of A and ignore the rest. So pi m is counting how many behaviors over A can I have by using H's in my class. So this is my function pi m of H is a kind of a function that characterizes the class H. And what can we say about this function right off the bat? We don't have to be very smart about it. What can we say about this function? We can say two things. First of all, if m is less than the VC dimension, then this function is 2 to the m. Note that if I count how many behaviors I have over a set of size m, the maximum number of 0, 1 behaviors is 2 to the m. I have m points. Each of them can get either 0 or 1. I have at most 2 to the m behaviors, right? But if the set is shattered, then I get all of those behaviors. So if my m is below the VC dimension, I have a shattered set of size VC dimension. So I have a size m with all the behaviors. So the maximum over all sets of size m is 2 to the m behavior. If the set is not shattered, so if m is bigger than the VC dimension, we know that it's not shattered, because the VC dimension is the biggest size of a shattered set. So if I'm above the VC dimension, I cannot shatter any set. What does it mean, not shatter? That I cannot get all of the behaviors. So this function should be less than 2 to the m above the VC dimension, and exactly 2 to the m below the VC dimension. Okay? This should be a clear point if you grasped what the function is. The function just counts behavior of the class H over A. If you can shatter such a set, because it's the maximum over all sets, so I can always pick a shattered set. So if you can shatter a set of this size, it's 2 to the m. If it's above your shattering ability, which means above the VC dimension, it's less than. So far, we didn't do anything. We put a definition and just made a trivial observation to just make sure that we understand the definition. And now comes the beauty of it. And the beauty of it is this theorem, the Sauer lemma. And again, it's something very interesting. I mean, even before you read the theorem, let's look at the title. Sauer, Shelach, Perles. It turns out, and again, it's the pre-internet era, that at the same year, in 1971, 3 different groups of mathematicians discovered the same result at the same time in 3 different places for 3 different contexts. So Vapnik and Chervonenkis discovered it in Russia for the purpose of doing machine learning. They didn't call it machine learning, they called it statistics. Sauer was a combinatorist that was living in Great Britain, and he discovered it in England. Shelach was my supervisor, and he was a logician in the Hebrew University in Jerusalem. He discovered it for the purposes of investigating logic. And Perles is a combinatorist in the Hebrew University, and he was doing combinatorics. So 4 different groups at the same year discovered the same result, each of them for a different application. And actually, Perles discovered it twice. He wrote a paper with this and forgot that he wrote a paper with this and wrote another paper. So it should be called the Sauer, Shelach, Perles lemma. And what does this lemma say? I mean, you know, mathematicians are supposed to be confused. So what does the lemma say? The lemma says that if you look at this shatter function, it is always bounded by the sum from I equals 0 to d of m choose I, which is at most m to the d. So this function is bounded by the number of subsets of size less than the VC dimension that the set has. If you have a set M, and I want to count how many subsets of size less than D it has, it is the sum of all sizes of M choose I. M choose I is how many subsets of size I do you have. And I allow you to count only subsets of size at most. Now, what is so special about this result? What is special about this result is a very useful, I don't know how to call it, kind of, when you do computer science, I guess most of you studied computer science, right? And when you study computer science and you go to some algorithms course, it seems like that there are only two types of functions. Either they are polynomial or they're exponential. But if you have a little bit of sense of mathematics, what does it mean either polynomial or exponential? What about the function 2 to the square root of n? What about the function n to the log n? What about tons of functions which are below exponential and above polynomial? What is this dichotomy that either you're polynomial or you're exponential? It doesn't make any sense. It's only computer scientists can come up with such a, but it's not only computer science, because if you look at this function, what does it do? What do we have here? We have here, if I want to draw the behavior of this function, if I want to draw here pi h of m, and here I have the size m, and this is going to be the VC dimension of the class h. How will my function behave? Right? So here is the number of subsets of size at most d. If m is below d, the number of subsets of size below d is all the subsets. So below d, it behaves like 2 to the m. Because if I count all the subsets of size less than d, I counted all the subsets, I have 2 to the m subsets. Above the VC dimension, it becomes the function bounded by m to the d. So what did I get? It is exponential here, and the minute it stopped being exponential, it became polynomial in m. It kind of satisfies this dichotomy that otherwise is completely false. You're either exponential if you're below the VC dimension, or you're polynomial if you're above the VC dimension. So it has this very nice dichotomy that we kind of intuitively assume, but it's not true in general. It's one of the very few cases where you have such a dichotomy. So is it clear that there's a big distinction here? I mean, at this point, it's the same. Because at the point of the VC dimension, you get here 2 to the d, and 2 to the d is exponential in your input d. It's also below m to the d. Because my function has to be below m to the d. That's what it tells me here. Right? So at this point, they agree. But on the sides of this point, to the left and to the right, we have this dichotomy between being exponential, becoming polynomial. So this is a completely combinatorial lemma. It just says the VC dimension gives me this very nice bound on the number of behaviors. Above this, it's just polynomial. So this is the key to showing that finite VC dimension implies learnability. Let me just demonstrate. I'm trying to convince you that this is an exciting result. And I know it's not easy to convince someone that something that you are excited about should also excite them. But let me show you one example. The example is the pizza example. So assume that you have a pizza, and the pizza has all kinds of things on it. So you have olives, and you have mushrooms, and you have tomatoes, and you have all kinds of things. And you have two people, and you want to divide the pizza between you, and you can only cut it in straight lines. And what I'm asking is, how many of the different partitionings of the pieces in the pizza can you cut with a straight line? What proportion of the different partitionings can be realized by a straight cut. You see what my question is? You have a collection of points, forgettable. You have a you have a collection of m points in R2, and I'm asking you sum of the partitions of these points into two sets. If I say all of these points are 0 and all of these points are 1, then I can realize it with a straight line. But if you can say this one is 0 and this one is 0 and this one is 1, then I cannot realize it with a straight cut. And I'm asking what proportion of the partitions can be realized with a straight cut. And the Sauer lemma tells me this is extremely small proportion. Because, so what do I need to, in order to apply Sauer lemma, what is the relevant class here? Straight lines, right? The relevant class is the class that we didn't talk about so far, which is half spaces. We call it half spaces in R2, which is the set of all H. W, well, W is a line, and we label as 1 everything above the line, and we label as 0 everything below the line. It's the most natural class in R2. You take a line, label above it as 0, and below it is 1. And it's very useful in machine learning. And what I'm looking at is how many partitions over a set of size m, how many behaviors do I have with this class? So in order to apply the Sauer lemma, what am I missing about the class? What do I need to know about this class? It's VC dimension. What do you think is the VC dimension of this class? What do you think is the VC dimension of half spaces in R2? Linear half spaces in R2. Okay, I'm suddenly we begin to hear quickly quick answers. Who was the volunteer now? Yes. What do you say? 3. Okay, so let's, in order to convince us that she is right, we need to do two things. We need to show a set of 3 points that half spaces can shatter, and we want to argue that you cannot shatter any 4 points. So can you show me 3 points that you can shatter? Any 3 points which are not on a line. Because for every partition, I can have a line that all of them are above. I can have a line that all of them are below. I can have a line that cuts any point and leaves the other one. Okay? So I can shatter 3. Why can't we shatter 4? That's a little bit more delicate. And there is kind of an argument that if I have 4 points, then either the 4 points are organized like this. If they're organized like this, then they cannot have the 3 here without taking the 0, the center with the half space. You cannot have a line that will do this. Okay? Or my 4 points, what is the other option of the 4 points? They look like this. And now what is missing when I'm trying to cut it with a straight line? What subset I cannot separate out? The diagonal. Right? If this is my set, there's no line that will pick these 2 points above it, and these 2 points will be below. This takes some argument. Why can't I shatter 4 points? But let's leave this argument. Let's believe it. So you're right. It's 3. So the VC dimension is 3. Now let's go back to this problem. I have m points in R2. I want to know how many partitions can I realize with a straight line. What does the Sauer lemma tells me? The Sauer lemma tells me the number of straight cuts is at most what? We have the lemma there. What? M cubed. Right? How many partitions? What is the total number of partitions of m points? Total number of partitions is 2 to the m. So if m, say m is 100, then, oh, say m is 10. It's good enough. Right? So here, the number of, if I want to know what partitions you can realize with a straight line, you can realize at most 1,000 partitions with a straight line out of 2 to the 10. Oh, this is not very impressive. This is very unimpressive. Okay, so let's say m is 100. So if m is 100, what I can realize with a straight line will be at most 10 to the 6, right? Which is a million, right? And what I have here is 2 to the 100, and now it's becoming really miserable. Because I have 10 to the 6 divided by 10 to the, by 2 to the 100, which is roughly 10 to the 6 divided by 2, 30, which is 1 over 2 to the 24. So the fraction of partitions that you can realize with a straight line is ridiculously small. So when you're talking about why do I emphasize it? This was discovered before the Waffen-Journalist dimension, just about the straight lines. It was Tom Cover is a guy that, I don't know if you saw it, there's a very famous book on pattern recognition by Cover and Thomas. Anyway, so Tom Cover was a mathematician that was doing statistics and pattern recognition, and he was going against this trend of statisticians that everything is linear. Linear regression solves all our problems. And he wanted to say, you can express nothing with linear. I mean, if you have m points, if you only have 100 points, already what you can express with a linear partition is ridiculous, nothing. And this is only part of the Sauer lemma that generalizes it to any class of a finite dimension. Okay, so how are we time-wise? Oh, we are out of time. I'm just beginning to enjoy. Okay, so we have time tomorrow morning to continue. Okay, so thank you very much and enjoy the evening.